So now let's learn of the transfer of control addressing modes, right? As we have discussed very briefly when we discussed about the transfer of control addressing modes, they're mostly used to transfer the control. Imagine I have some code like this, right? So imagine if I have some code like this, right? So this is one instruction, other instruction, other instruction. After executing this instruction in the sequential form, after executing this instruction, I'll execute this instruction. But the transfer of control basically means after executing this, if I want to execute this instruction, let's assume I want to execute this instruction, right? This is again, if I want to do that, we have seen how something like jump 0. So we have seen instructions like this, right? Jump. So in C programming language, this is equivalent to goto statements. In goto statements, what can I do? I can have a label for, so if you think about it from a high level programming perspective, right? I can have something like go to some L, and I can have label L here, right? I can have this label here, and I can have some instructions here. So what happens here? After all these lines are executed, after all these lines are executed, as soon as there is a go to, this will now, the control will directly go from here to here, right? So these are also called as jump instructions or branching instructions. Okay, again, these two terms are used interchangeably, or sometimes they're also referred to as go-to instructions, right? So these are called as unconditional instructions. There are two types of jump instruction. There is something called as unconditional jump, and there is something called as conditional jump, right? In conditional jump or conditional branch statements, you check a condition. For example, you could say jump if 0 to some address, okay, to some address, okay? I can give some address here, and I can say jump if 0. How does this work? Here you are conditioning, or you are saying if the 0 flag in the PSW, if the 0 flag in PSW equals to 1, if this is 1, or if the accumulator value equals to 0, only then jump to this address. That's what you're saying. So these are called as conditional jumps, or jump if not 0, and things like that. So you have unconditional jumps, wherein unconditional jumps are like your go-to statements in C programming language, which are not very often used in practice because they can be very, very hard to understand what's happening, right? So if you have a go-to statement, the easiest way to implement this in machine level language is by using jump or branch or unconditional jump statements. On the other hand, you have your for loops, right? Look at your for loops, right? This is your for loop. So you have a condition that you check as part of your for loop, right? In C programming, you check a condition. If the condition is false, then you directly jump to the line that is after the for loop. If the condition is true, you go into the for loop and execute these statements. So this for loop can be converted into conditional jump statements. Similarly, while loop also, if the condition in the while loop is true, so you have things like this, right? If the while loop condition is true, whatever condition here, then you execute this. If it is false, then you execute right, you jump directly after these instructions, right? So broadly speaking, the transfer of control can happen using unconditional jumps or conditional jumps. And now coming to the addressing mode itself, there are broadly two types of addressing modes. One is called the program counter relative addressing mode. Remember, the program counter always has the address of the next instruction that we want to execute, right? So this is sometimes referred to as PC relative addressing mode or simply relative addressing mode. Okay, that's one type of addressing mode, especially in the context of transfer of control, right? The second type of transfer of control addressing mode is called based or base register addressing mode. So we'll understand both of them in lots of detail. But before we go there, we have to understand one small concept about memory organization called as segmented memory. Again, this concept, there are a lot of concepts that we learn in operating system also. In operating systems, we learn about concepts called as paging, segmentation, virtual memory, right? Virtual memory, etc. in lots of detail. Here, I'm not going too deep into why we need segmented memory, why are we using segmented memory, how segmented memory is implemented. I'm not going into the details of it. In our operating systems course, you will learn a lot more. There is literally a whole chapter with, I think, with at least 15-20 videos where we go into understanding how paging works, what is segmented paging, how virtual machine, how virtual memory, my bad. I keep reading VM as virtual machine. That's also a concept in operating system. But in the context of memory, this is called as virtual memory. How all these concepts are actually implemented, we'll study them in detail in operating system. Here, if If you have studied operating system, you already know what is segmented memory or segmented paging memory. You already know that. But here what I'll do here is, if you don't know that concept, if you have not studied that concept in operating system, I'll give you a high level overview of how memory is organized as segments. But for more details, you should check out the contents in the operating systems course. Okay. So here I'll give you a brief overview. Okay. So imagine this is my whole memory. My memory addresses start from 00000 to hexadecimal FFFFF. Each hexadecimal digit corresponds to 4 bits. So this is a 20-bit address. So my address is 20-bit address. Right? My address to this memory is 20-bit. So there are 2 power 20 cells. There are 2 power 20 cells or words, right? If each word is 1 byte, let's just assume that if each word is 1 byte, I have 1 megabyte of memory. 1 megabyte of memory that I have here. So what is done typically in the concept of segmented memory is, I break this into equal size segments here. I break it into segments, right? So let's assume I break this into, let's just say, if I want to break this into 16 equal sized segments. So if I want to break this into 16 equal sized segments. So think of each of these green boxes as one segment. So this is my segment 0. Okay, so let me write this. This is my segment 0, my segment 1, so on and so forth, my segment 15. Right? If I want to break this into 16 segments, what is the size of each segment now? Let's see. So I have 2 power 20 cells. So 2 power 20 by 2 power 4, because 16 is 2 power 4. So this is 2 power 16. What is 2 power 16? 2 power 6 is 64. 64 kilobytes in each segment. 64 kilobytes in each segment. Now for each segment, look at this. My total addresses are 20 bits. Now I'll break this 20 bits address into 2 parts. I'll use the first 4 bits. I'll use the first 4 bits to represent the segment. So this is segment 1, segment 2, segment 3, segment F. Okay, look at this. I have 5. Look at this. I have 5 hexadecimal digits. This is 4 bits. 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 So the first 4 bits, I will use it to get my segment number. I will use it to get my segment number. Right? So this next 16 bits, I will use them for my segment offset. So the way it will work is this. Okay. So let me give you an example. Imagine if I'm given this address 1F00 in hexadecimal. So the first one I'll interpret it as the segment number. This 1 corresponds to the segment which starts with 1. So within this segment 1, this address, what is this address now? This address is 1 followed by 0000 up to 1 followed by FFFF. Right? That's what are the segment addresses here, right? So this is my segment number. This is my offset within the segment. See, within the segment, I have to go to, so base address. So the base address of this segment will be 1000 in hexadecimal. And the offset here is this F000. Right? So this is called the base address. The base address is the first address in the segment. Offset is how many words or cells am I away. So this location will be 1F000. Right? So 1F000, sorry, 1F000, not 00. I'm sorry, 000, because I have 20 bits, right? The first one is used as segment number. The rest of them are used as segment offset. Again, we discuss why we need segmented memory, all these concepts in lot of detail in operating system. I'm not going into the depths of it right now, right? Because we have discussed it in lots of detail in operating system. I'm just giving you an overview of how segmented memory works and how do we address segmented memory. So given any segmented memory, I have the segment number and the segment offset. Segment offset basically says from the very base address or from the very first address. This first address is called the base address, right? And the number of bytes you have as offset, that's called the offset. So F000 is your offset, right? And your base address is 1000. This is the base address or the first address of this segment, right? Very, very important. Okay. So given that you have some idea of segmented memory, but again, you will get much more detailed idea when you read the concepts in operating system. Okay. Now let's go into the addressing modes. Now things will become much more easy for me to explain these addressing modes. So imagine if I have some code like this. Okay, let's take a simple example. Okay, so this green cell here, this green cell, this is one segment. So this is, let's say, some segment. This is one segment. This is another segment. So if you want to jump from within the segment or intra segment, if you want to jump intra segment, which means you want to stay in the same segment itself. You're just jumping from one location to other location in the same segment. In such a case, PC relative addressing mode is what is used extensively. I'll explain you how this works, the internal workings of it. It's actually very easy to understand. Okay, so imagine this address, this jump. Okay, so what happens here is I'll have jump, some number here, and when I jump, it will take me. Again, this is unconditional. I'm talking about unconditional jump. You could also have conditional jumps. Conditional jumps, just check a condition. If that condition is true, then they will jump, or else they won't jump. So in this case, jump L, imagine this address is 2080. Suppose this address is 2080. Okay, I'll tell you how this L itself comes into the play. Okay, that L in the case of PC relative addressing mode is called the relative address. I'll explain you how the whole thing works. This effectively jumps as soon as this instruction is executed. Instead of executing the next instruction, we directly jump to this instruction, which corresponds to this L. Now, how do you encode this L? That's very, very important. Okay, so let's look at this example. Imagine I have 2080 jump some address. So this is my address part. Okay, so this part, this is my opcode part, this is my opcode part, and this is my address part. Now, while this, look at this, while this is being executed, what is the value stored in my program counter? My program counter always stores the address of the next instruction. So while executing this line, you store in your program counter 2084. Let's just assume these numbers are all in decimal, just for simplicity. Let's assume all these are decimal addresses. Just for simplicity. Okay, so the program counter always has this. Now what, see, at this point, let's assume this is an unconditional jump, right? So you say jump, and you want to, let's say, jump to the 4000 location. You want to jump to address 4000 in decimal. Let's assume all these addresses are in decimal so that the math becomes easier. Okay, suppose you want to jump to address 4000. Now what value will you store in this relative address or the address field? You basically say how much should be added to program counter to reach this destination that I want to reach. So what gets added here is 4000 minus 2084, whatever this value is. Okay, so 4000 minus 2084, whatever this value is what? So let's assume these are simple integers, or these are simple numbers. So this becomes 16, right? So, and you get 1916, right? So 16 plus 84 is 100. So 100 plus 20, 19, 39, yes, 4000. If these are decimal numbers. So what you store in your relative address, what you store in the address here is not the absolute address of 4000. You store 1916 here. Suppose 1916 is stored here. So how does it work? Whatever is there in this address field gets added to the program counter. Okay, so 2084 plus 1916, that will result in address 4000, which means after executing this line, we will directly jump to line 4000 and execute the instructions at line 4000. That's how it works. Again, this is called PC relative because this address that I have is relative to the program counter. It simply says how much should I add to the program counter to obtain the actual effective address of where I want to land. So the effective address in this case, again here the effective address is not the address of data, it is the address of the next instruction. So this is very important. In the case of transfer of control addressing mode, we are getting the effective addresses are mostly the addresses of the next instruction, not data. So in this case, we only care about the effective address of the next instruction. And how do we get it? The effective address of the next instruction is whatever is the current value of program counter, add it to whatever is there in the address field. This is my effective address. This is where I want to jump to. So your program counter gets added to 1916, it gets updated, and then as soon as it gets updated, what happens? As soon as this instruction is run, whatever is the value of program counter will go there. So my control directly jumps from 2080 to 4000 line. That's how this works. Right? Very, very important. Okay. And again, PC relative addressing modes are used when you want to jump into the same segment. In the real world, again, this is a concept that we learn in operating systems. So this in one segment, I store one logical chunk of code. Maybe a few functions that are most used, I could store it in one chunk or in one segment, right? In one segment, I might end up storing a bunch of related functions. in another segment, I could have a bunch of other functions also. So your jump, again, even calling a function is a jump. If you think about it, even calling a function needs you to jump to a different location. So PC relative addressing mode works perfectly if you want to jump within the same segment. But if you want to jump to a different segment, we could use the base register or the base address addressing mode. Okay. So base address addressing mode or based addressing mode is often used when you want to jump from, let's say, this segment. Let's assume this is one segment. If I want to jump to this segment, how do I do it? Right. So this is inter-segment jumps. This is your inter-segment jumps or inter-segment branching or inter-segment go-tos. Right. Now often, look at this. So as I told you, typically what happens in the real world, again, you'll understand some of this in compiler design, some of this in operating systems especially. So some related functions are stored in one segment, other functions could be stored in other segments. Right? Again, each segment is typically a few kilobytes in reality. Okay. Again, there is segmented paging and all the concepts that we study in lots of detail in operating system. I'm not redoing the same thing here because that's a big topic in itself. Right. So that's why I've just given you a high level overview that memory is segmented in reality into pages or segments and all that concept. Okay. Again, paging is a very, very important concept in operating systems. Okay. Coming back to the organization here. So how does the base address addressing mode works? This is slightly interesting. So this says my effective address of the next instruction is whatever is my base address of the segment that I want to jump into. For example, if I want to jump from here, let's say, suppose this instruction is executing, if I want to jump here, let's assume this absolute address is 12345 hexadecimal. Let's assume this is where I want to jump. Now, instead of saying, let's say my program counter will be pointing to this. Instead of subtracting 12345 minus my program counter, minus this address, right? What is done here is I have something called as a base register. In the base register, I store the base address of the segment that I want to jump into. So I want to jump from this segment to this segment. What is the base address of this segment? The base address of this segment is 10000. That's the base address of this segment. What is the base address? It is a segment. It is the address of the first byte. It's the starting address of this whole segment. Right? So my base address is stored in base register and that value is 10000 in hexadecimal. My address offset itself. So my instruction will say jump. Look at this. My instruction could say jump. Right? The base register, whatever is stored in the base address, which is stored in a base register, and an offset. Right? So these two constitute the final address that I have. So the base register will store the base address of the segment that I want to go into. Right? Once I have this, now I'll say, okay, what is the offset here? The offset here from this line to this line, the offset is 2345. So my address offset is 2345. Okay. So the way this instruction will look like is it will have jump. It will give me the base register, some register where the base address is stored. So I could have this. I could have something like this. Jump R1 2345. Here I'm assuming that this register R1 has the value 10000. Okay, so now this addressing mode is your base address addressing mode. Okay, or it's also sometimes referred to as simply based addressing mode, because we are using the base address of the segment itself. So now what does it do? It takes this address, adds this offset, and this will determine where you have to jump to. Very simple concept. Now look at this. Both PC relative addressing modes and base address addressing modes are extremely popular in the modern world wherever you have jump statements, because we want to be able to perform program relocation at runtime. So there's something called as dynamic program relocation. Okay, so what does this mean? Again, this is something that we've discussed in operating system, but I'll give you a brief overview here. So what this means here is, imagine I have a program, some functions are loaded in this. Imagine some functions are loaded in this segment, some functions are loaded in this segment. For some reason, let's assume this program that I'm executing, which is often called as the process, A program under execution is called as a process. Suppose this process or the program which is being executed have to give up this segment for some reason. Again, those reasons we explain in operating systems, right? Suppose it has to give up this page or this segment, right? Then what happens? The program gives up, or the process which is actually currently executing gives up this segment, and all the code that is here, because this is now, see, currently let's assume there is a program 1. Suppose there is a program, or if you don't know what a process is nothing but a program which is currently being executed. Suppose imagine I have two processes, P1, P2. Let's assume P1 currently is loaded in this and in this. Now let's assume process P2 comes in and says, I want this segment. And why does it do that? We'll understand that in operating system, right? We discussed this in operating system in lots of detail. So let's assume P2 says, I want this segment. Then what the operating system does is, operating system takes all of the contents in this page, copies them to a different page, copies them. So that is what is called as dynamic relocation. This process code is now relocated from these memory locations to these memory locations. So P1 is now reloaded into this, right? While P2 now gets control of this, and P2's all the instructions, all the variables of P2 will get loaded here. But now what happens here is, if you have PC relative addressing mode and base address addressing mode, by relocating this nothing will happen. If I want to jump within this, if I want to jump within the same segment, I don't care what is my base address anyway. I don't care about it, because in my PC relative addressing mode, I'm just adding to my program counter. That's it. I'll simply add to whatever. See, if this instruction is being executed, my program counter is pointing to this. I don't care in which segment my process is loaded, right? If you are using PC relative addressing mode. Similarly, if you have to jump, so let's assume if you have to jump from here to some other segment here, even then I don't care in which segment my program is loaded. My program could have been loaded here, my program could have been loaded here, because to jump I'm going to use this base address and this offset, right? So base address addressing mode or based addressing mode and PC relative addressing mode, they help you to perform program dynamic relocation or dynamic process relocation, which means you can, the operating system, not you, but the operating system can move around your program from one segment to other segment very, very easily without disrupting the execution of the program significantly. Everything will still work, right? This is very, very important concept as far as addressing modes is concerned.